Okay, today we're going to cover Chapter 19, Plate Tectonics, the Unifying Theory. Let's put it this way. Plate tectonics is to geology what evolution is to biology. You cannot realistically study one without the other on the Earth itself. So plate tectonics is an idea that we've been touching on throughout this course, and now we're going to try to bring it all together. Okay? So, where do we start? Well, we start with the idea of continental drift. A gentleman by the name of Alfred Wegener, whose name I've mentioned a couple of times already, first proposed the idea of continental drift as a hypothesis back in 1915 when he published a book called The Origin of Continents and Oceans. This was based on a lot of his observations of the natural world in terms of time he spent in the Arctic as a meteorologist, watching the way ice flows broke apart and came back together, looking at a number of different features, which we'll talk about here in just a moment. But he came up with this idea that the continents are moving through time across the surface of the Earth. So in his idea, his hypothesis said that around 200 million years ago, there was one giant supercontinent that he called Pangaea, which stands for all land in ancient Greek. And that about 200 million years ago, this supercontinent began to break apart. And after it broke up, the resulting continents then drifted into their current positions. So, what evidence did he have for this? Well, the best evidence he had at the beginning was the fit of the continents. If you look at the Earth, and this is a poor representation, I should have grabbed a globe, but if you look at the Earth, you can see how it looks like certain continents, especially along the Atlantic Ocean, should fit together. Okay? They should puzzle piece together. Now, the interesting thing is that Wegener was basing this on the coastlines of the continents, what you could see. However, we now know today that if we use the seaward edge of the continental shelf, i.e. the point where the continental shelf transitions to the continental slope, the fit is even better. So we know that these continents can fit together like a jigsaw puzzle. He also had fossil evidence, specifically several widespread fossils, but the two specific ones that he really brought up was one called a Mezzo Saurus, which was a small, probably aquatic reptile on the order of about 1.5 to 2 feet long. Looks like it probably swam in shallow seas and ate fish. But it's found on either side of the Atlantic. You find its fossils in Africa and you find its fossils in South America. An animal that small, that isn't fully aquatic, typically isn't going to go fully across the Atlantic Ocean as it is today. He also had a plant called Glopteris. This is a plant that was identified because of its very large seeds, kind of akin to today's cycads, to give you kind of an idea of what it looked like, though it's not really a cycad per se. But it's also found either side of the Atlantic Ocean. Now, the question is how many plants today produce seeds that can travel on the open ocean? Generally speaking, there's only one most people can think of, and that is the coconut. And even those seeds can only last for a short period of time and couldn't really make the trek of crossing an ocean the size of the Atlantic. And then there's rock types and structural similarities. It's very interesting that rocks and physical structures like mountain ranges can actually be matched across the Atlantic Ocean. There are mountain ranges that are comparable in age and structure to the Appalachians in the U.S. that are found in the British Isles and Scandinavia. In fact, they seem to have the same rock units, they seem to have some of the same structural features, and the same weathering patterns. More importantly, though, is basalt units in Africa and South America. Now, Wegener didn't know this at the time, but there are basalt units that he saw that looked very identical. In fact, they looked almost identical. They didn't seem to have any sort of point of origin that could be located, but the rocks looked virtually identical in terms of their thickness, in terms of their structure, just flowing in opposite directions. More importantly, though, is we fast forward to more modern day time when we started doing the geochemistry of the rocks. And one of the things that we find is that the chemistry of those igneous rocks is essentially identical. That is unusual. You only get identically chemical igneous rocks from the same source material. So you cannot have two volcanoes in different locations have chemically identical signatures. So this indicated even more strongly in modern times that we're dealing with a single source for this magma or for this lava unit. And then there's paleoclimatic evidence. There's evidence for late Paleozoic glaciation near the equator, which doesn't make a lot of sense. If the landmass is at the equator now, but at that same time we see areas that are now up in the northern latitudes or southern latitudes that appear to have a tropical climate. It doesn't make any sense for the poles to be tropical and the equator to be Arctic in nature. So there's something going on here that has to be explained by the continents moving, not by some bizarre weather pattern setup. And then you have the fossils that are the major coal fields in the eastern U.S., which indicate swamps and warm tropical areas in these regions. Now, somewhere around 1924, there was a great debate about the Continental Drift hypothesis. Part of this debate was driven by the fact that Wegener had no way to provide a mechanism to allow the continents to move. He tried a few proposals. He tried thinking that maybe tidal influence did it, but if the tidal influence was strong enough to cause the continents to move, it would be enough to actually stop the Earth's rotation. I mean, you couldn't have that much force working on the surface of the Earth without causing something else to happen. Wegener suggested that the continents move through the ocean crust like an icebreaker, but you would expect to find the evidence of that, the broken up crust left behind, and that wasn't seen. So what we end up with is a hypothesis that fits the evidence of the observations, but the mechanism for how to perform the operation of the hypothesis just isn't present. So basically, from a scientific standpoint, Wegener's idea failed to meet the proper test of the scientific method. Now, generally speaking, even though he had the supporting evidence, widespread acceptance did not occur. A few people considered Wegener's ideas plausible and continued the search for how can the continents move, but for the most part, his idea was pretty much thought of as a dead end. Now, fast forward a little over 30 years to the 50s and the 60s, and we start getting some new evidence coming in line. The initial impetus for renewed interest in continental drift came from rock magnetism, or what we call paleomagnetism. Basically, let me grab something. As you recall, we have minerals that are somewhat magnetic in nature. This is a jar that is full of magnetic sand. It's kind of hard to see it. There we go. So you can see the sand. Okay, these are mineral grains that formed in igneous rocks and then have been weathered out. Okay, so this is magnetite and hematite mostly. When these grains form in the rock, when the rock is molten, they have a tendency to align themselves with the current magnetic field of the Earth. So ancient rocks can actually preserve the magnetism that was occurring on the Earth at the time of their formation. Now, this means that we can actually figure out from a point of north to south where those rocks formed. So let me show you how that works. So basically, if we take the idea that the Earth has a giant bar magnet in it, like this, okay? There's north, there's south. And then we have the lines of magnetic force. Now, those lines of magnetic force are going to move in a specific way. So let's just say that they come out of the Earth and they wrap around the Earth. Now, the way they're going to come out is we're going to say they come out of the South Pole and they go into the North Pole. Okay? Sort of like that. All right? So, here's what happens. We have the rock mineral, the rock form. We have magma or lava, and the minerals then begin to crystallize out. And as long as the environment that they're crystallizing in remains fluid, they can align themselves. So magnets now, remember, will align themselves with opposites. So opposites attract in magnets. So a south pole is attracted to a north pole. So if we were to have a mineral grain form near the equator today, what we should see is that the grain should have a nearly horizontal orientation with its south pole pointing towards the magnetic north pole and its north pole pointing towards the magnetic south pole. This means that no matter where we're at on the surface of the Earth or near the surface of the Earth, the orientation of the grain with respect to horizontal is going to relate to the magnetic field in the area. So if you had a rock that formed near the South Pole, the orientation of the magnet or the mineral should be vertical instead of horizontal, and its north pole should be pointing down and the south pole should be pointing up. Same thing at the North Pole, but reverse. So the South Pole was pointing down and the North Pole was pointing up. So no matter how we move the magnet around the Earth, the result is that the magnetic grain the magnetic field is going to orient based on the field of the Earth itself. So we can measure that angle of deflection and measure the direction of north and see where on the Earth, in terms of from north to south, that rock formed. So this gives us a means of determining the origin of the latitude of origin of the rock. Now, one of the things this brought up is when we started doing this and started looking at rocks in general, one of the things that we saw is something called polar wander. What polar wander is the apparent movement of the magnetic North Pole over time. I've got this figure in your book. It's on page 5. Let's get it so you can see it. 459, and it shows basically these two curves. Now, these curves are the apparent wander of the magnetic North Pole, but taken for different continents of land or different locations on the Earth. And what this indicates, this one's European and this one's North American. So this one's North American, that one's European. So it shows that there's a separation in those curves. Now, one way to take that is that, well, that means those curves, that would indicate that there was two magnetic North Poles. Does that make sense? Two poles? Not given the way we know the magnetic field of the Earth is generated. So the only way to correct for this is to have the two continents move. And as we move the continents, so we put the poles together at the same temporal time, we can see how the continents must have been moving around the Earth. So all of a sudden, we're having this evidence that is indicating that the continents were moving. This is evidence that Wegener did not know about. So the polar wander curves for North America and Europe have similar paths, but are separated by about 24 degrees of longitude. If the differences between the paths can be reconciled, if we put the continents in place next to each other, and it can show that the separation of the continents increased over time. Now, also during this time, during the 50s and 60s, we had technological strides that led to an extensive mapping of the seafloor. The federal government at the time was very interested in mapping the seafloor. In fact, side point here, most of the seafloor in many areas of the world were actually considered to be a national security secret for a long period of time because of the fact that they had routes for submarines through those areas. Go figure. Okay, but the technology increased. The sonar scanning became better. We began to get better feeling for what the seafloor is looking like. This began to show the things that we talked about last time in the chapter on the seafloor, such as the fact that the layer of sediment on the seafloor gets thinner the closer to the ridge you get, and gets thicker the further away from the ridge you get. The rocks actually get younger at the ridge and older further away from the ridge, as well as the fact that we have this thing called geomagnetic reversals. We find that in the rocks, as we are able to detect the magnetic field preserved within the rocks, we now find that periodically the magnetic field of the Earth flips, does a full 180. We don't know how fast this occurs in yet. It seems to be very rapid, but it happens very quickly for all intents and purposes. And it's happened thousands of times, literally. But what we see is that there are periods of time where you can walk outside if you had a regular compass, and all of a sudden north would be pointing towards Mexico, not further into the States. Or if you're standing near our classroom, it'd be pointing towards the Santa Ritas, almost over Mount Benedict, where all the radar or the TV and antennas are. So we get these reversals that happen over time. So rocks actually exhibit this. Now, some of our technology was actually being able to map the magnetic field of the rocks in the seafloor. This is in part very interesting because it's an anomaly that when it was first found that the field is reversing. It's like, why would that happen? And so they looked for it and see, was this a one-time thing? Was this just something that was localized for some bizarre reason? Or was this phenomenon worldwide? Well, long story short, it's worldwide. So what we have is rocks that exhibit the same magnetism as we experience today. We consider normal I can't say it now. Polarity. There we go. Polarity. And rocks with the opposite magnetic field are said to have reverse polarity. Now, the dates when the polarity of the magnetism changed was taken by sampling the rocks in lava flows in the seafloor and doing their absolute age through radiometric age dating. What we see is that these geomagnetic reversals are recorded within the crust. In 1963, Fred Vine and D. Matthews tied the discovery of the magnetic stripes to the ocean ridges to the concept that Harry Hess came up with of seafloor spreading. Now, what Hess's concept was is in the early 60s is that we have these ridges that are located above zones of mantle upwelling, and that new seafloor is created there, and the material moves away conveyor belt style to open up the area to allow more seafloor to form, and then ultimately at the deep trenches, that seafloor subducts back into the earth and gets recycled. So you have this conveyor belt. Well, Vine and Matthews tied their magnetic reversal evidence to this as well, because Hess's idea of seafloor spreading explains the fact that when we look at the magnetic reverse pattern, one of the very interesting things that we see with it is that this pattern is mirrored, for all intents and purposes, on the mid-oceanic ridges. Now, let's see if I got a good photo of that for you. Yeah. So, that one's not going to show it to you. Let me grab it out of this book. So the interesting thing is that when we look at these, it's almost a mirror pattern. This should be in this book still. Or did they take it out of this one? So they took it out of this one. Now, it kind of looks like this. From your book, page 464, I wanted to show you on the Earth itself, but you have these periods of normal, reverse, and they're mirrored across the spreading ridge. So, with this, what happened is there was a combining of the idea of continental drift with seafloor spreading. This formed the backbone of the hypothesis, now theory, of plate tectonics. Plate tectonics is a paradigm, a new paradigm that shifts our understanding of geology greatly. Literally, the world of geology prior to plate tectonics had completely different understandings for how certain things, especially mountain building, volcanism, earthquakes, actually occur, versus today, where we now have a greater understanding of how they're all interrelated. The composite of the various ideas help to explain the motion that's observed in the Earth's lithosphere over time through the mechanisms of subduction and seafloor spreading. So the continents, instead of plowing through like Wegener said, they're actually sort of like floating on the oceanic crust, or floating in the oceanic crust, being moved around by the oceanic crust as the oceanic crust is moving around. Now, when we look at the Earth today, the Earth's lithosphere, we see that the outer layer of the Earth, which again, remember, is composed of the crust plus the uppermost mantle, down to about 660 or so kilometers below the surface of the Earth. This is a rigid layer, and it's fairly solid and behaves like a rigid material, which means when it breaks brittly. This is overlying a weaker layer in the mantle, what we call the asthenosphere. The asthenosphere is partially molten and allows for the decoupling. And actually, I said that wrong. The lithosphere goes down to about 200 kilometers or so. The asthenosphere goes down to about 660. So this weaker layer allows for the lithosphere on top to kind of slide around on it. It's not perfectly decoupled. It's not that there's free movement by the lithosphere. It's just that it's capable of some degree of movement freedom. So when we look at the Earth itself, right now there are 7 major plates that make up the Earth, the plate tectonic system. This image is from a different book, but it's a really nice one that I like, that shows the different plates on the Earth laid out, as well as the different plate boundaries here. So we have the North American, the South American, the Pacific, the African, the Eurasian. Hint, Eurasian, Europe and Asia, technically one continent, physically speaking. The Australian and the Antarctic plates. These plates are constantly in motion. They're constantly changing size and shape. Now, the largest of the plates currently is the Pacific Plate. The smallest of the plates are probably the Juan de Fuca is probably the smallest one that we have mentioned on here. Yeah, the Juan de Fuca is shown as the smallest one. But there are a number of smaller plates, but the major plates are those 7: North American, South American, Pacific, African, Eurasian, Antarctic, and Australian. The plates move relative to each other, and so the motions are usually taken as relative to each other. Average is about 5 centimeters per year. Ultimately, it's driven by the unequal distribution of heat within the Earth. Remember, the interior of the Earth is much hotter than the exterior, so you have this convection, this internal convection that's moving. And so you can imagine that the convecting mantle under the plate is applying a bit of a drag force. Sort of like if you have a loose piece of paper and you kind of drag something along it without pressing hard on it. So you have a little bit of friction, but you're moving on top of the paper, and the paper then begins to move as well. The cooler, denser slabs of the oceanic lithosphere ultimately will descend back into the mantle where they're going to be recycled. Grinding along the plates generates earthquakes, it generates volcanoes, and it will deform the rock masses. So plate tectonics explains why we see mountains where we see them, why we see volcanoes where we see them for the most part, and why we see earthquakes where we see them for the most part. This is a very powerful theory. It unifies much of what we've been talking about over the course of this semester so far. So, plate boundaries. At the boundaries of these plates are going to interact. The nature of that interaction is going to determine what sort of geology we can see at those boundaries. So there's only 3 types of boundaries when it comes to the plates. There's divergent boundaries where the plates are pulling apart. There are convergent boundaries where the one plate is subducting under another, actually more like that. And there are transform boundaries where the plates are moving past each other laterally. So divergent boundaries is usually the ridges. This is where we have upwelling of material from the mantle that creates new seafloor. The convergent boundaries, which are destructive, are our subduction zones, our subduction trenches. This is where the plates are moving together, and there's usually 3 different types of interactions that we can see there. And we're going to go over these in a little more detail in just a minute, so I'm just going to mention that there's 3 and we'll come back to it. Technically 2 if you really want to get really technical about it, but 2 of them take a long time to see that they're actually 1. Then there's the transform boundaries where the boundaries are conservative. Nothing's created, nothing's destroyed. They just grind past each other. Every plate is bounded by some combination of those 3 boundaries, no matter what. New plate boundaries can be created in response to changes in the forces acting on the rigid slabs. There are some things that we still don't know how they happen. For example, we understand how a new divergent boundary or spreading center can occur. We don't really have a good handle on how a new convergent boundary can form. There are some issues with that from a geophysical standpoint that just don't make a lot of sense yet. So let's go through the boundaries really quickly, and especially the divergent boundaries, because we touched on these quite a bit in chapter 18. So here in chapter 19, I don't need to touch on as much. So the divergent boundaries are the crest of the oceanic ridges, and it's thought of. You can think of it as a constructive boundary. We're making new continental lithosphere, or not continental, new oceanic lithosphere. So with the ridges and the seafloor spreading, we see that these are, again, the longest features on the Earth's surface, topographically speaking, and make up over 70,000 miles of the Earth's surface. The crest is commonly 2 to 3 kilometers high. higher than the adjacent ocean, so you can think of it as a ridge, although maybe more like that. Again, it's 20% of the Earth's surface, winds through all the oceans. They range anywhere from 1,000 kilometers wide to 4,000 kilometers wide. They tend to have rift valleys depending on how fast they're opening up. In some cases, those rift valleys are are shallower. If it's spreading very fast, it tends to be more of a Horst and Graben type of environment. But if it's spreading slowly, it tends to be a deep valley. We see new sea floors created. Again, typical rates are about 5 centimeters or 2 inches a year. No ocean floor on the face of the Earth has ever been dated to exceed 180 million years old. New floor material is added equally on both of the divergent boundaries, so the spreading is equal across. We see topographic differences based on the spreading rates. Again, when we're at a slow rate of 1 to 5 centimeters a year, we have a prominent rift valley, like we talked about last time. It can be anywhere from 30 to 50 kilometers across, 1,500 to 3,000 meters deep, very rugged topographically. At intermediate rates of 5 to 9 centimeters a year, the rift valleys tend to be more shallow, maybe only about 200 meters deep, and topographically smoother. At fast rates greater than 9 centimeters a year, there's usually no median rift, though sometimes there's a Horst and Graben type of sequence that's there. They usually tend to be narrow, only about 10 kilometers wide, extensively faulted, and so forth and so on. And then, of course, we have the Continental Rifts, which are new areas of divergent boundaries trying to form under a continental landmass, trying to split the landmass into parts. Again, examples of that are the East African Rift, the Basalt Rift, the Rhine Valley, the Rio Grande Rift Valley. It's extensional forces trying to pull the continent apart. But not all rift valleys actually become full-fledged spreading centers. There are a number of them that fail. There's one up in the central U.S. that runs from Lake Superior down to Oklahoma. This is along the line where the New Madrid Fault occurred back in the 1800s. Major earthquake, about an 8.0 on the magnitude scale, happened, actually caused the Mississippi River to flow backwards, actually caused one area of the Mississippi River to change its course by over almost a mile, rang bells as far away as Boston and New York City. So major earthquake, but it was associated, now we know, with this failed rift valley. All right, so that's the spreading centers. Again, we covered a lot of this in chapter 18, so I felt like we can go over this fairly quickly because we're just rehashing the same thing we talked about last time. Convergent plate boundaries. This is where the older boundaries are returning into the mantle. The surface expression is usually through a descending plate, through a trench that can be thousands of kilometers long, usually anywhere from 8 to 12 kilometers deep, and between 50 and 100 kilometers wide. We call them subduction zones because that's what's happening. The material is subducting back into the earth. An average is for these is that the oceanic crust that's descending, the oceanic lithosphere that's descending, is going down at an angle of about 45 degrees. Though that angle is only an average. Where we are closer to the actual ridge, the subduction angle is much shallower. The further away we get from the ridge, the subduction angle becomes deeper. Although basically have the same characteristics, the features can be very variable. Now, there are primarily what I want to call 3 types of convergent zones. The first of these is going to be the ocean-to-ocean convergent zone. So this is where we basically have an ocean plate subducting under an ocean plate. So to draw that out for us very quickly, all right. So basically, the way it would look in its anatomy would be something like this. We have one ocean plate overriding another oceanic lithospheric plate. And from that, we get some sort of melting that occurs. Again, remember, as the plate is going down, it's going to take water with it. If you remember, water lowers the melting temperature of the rock, allowing the rock to melt earlier, which will create a magma source, which then creates a volcano above the right point, above the subduction zone, wherever it reaches the point where it gets to that melting phase, which depends on the angle that this is occurring at. So this can be closer for older plates, further away for younger plates that are subducting. But it creates this volcanic island arc, is what we call it, this line of volcanoes. One of the things that we can tell with this is the apparent age of the subduction zone, based on the volcanic islands that are created. If you look at the Gulf of Mexico, Atlantic Ocean, where the Caribbean islands are, most of the Caribbean islands are actually volcanic islands. They're forming as volcanoes over a subduction zone. And most of them are only 1 to 3 volcanoes that have merged together to form one island. Compare that to Japan. Japan is also over a subduction zone. You also have a volcanic island arc that makes up all of Japan. But there you have hundreds, if not thousands, of volcanoes that have coalesced together to form those islands. So obviously that subduction zone is probably much older than the subduction zone that's creating the Caribbean islands. Generally speaking, you get some degree of buckling that occurs there that will force up some of the land, but you don't get any compressive mountain building per se. That would happen with a continental to oceanic conversion. So in that, instead of having an oceanic lithosphere as the overriding lithosphere, we have continental lithosphere. And we may or may not, depending on how thick the thick stuff gets, have some volcanoes, but we'll definitely have some igneous activity that's occurring. So in a continental to oceanic collision, you basically have the oceanic plate still subducting, but now you have a continental plate that's overriding. If there's any magmatism that is, or magmatic activity that's being generated by the water as it's in the subducting plate melting, that could most likely create igneous bodies such as plutons or batholiths, where you have the igneous body is cooling and condensing, or crystallizing within the crust, but only on rare occasions is it coming through and creating volcanoes. It's still called a volcanic arc for that line of volcanoes, but we call it a continental volcanic arc. Examples of that would be the Andes Mountains in South America and the Cascade Range of that runs from Northern California up through Washington into southern Canada. The Sierra Nevada of California are remnant of a former volcanic arc. Now, over time, that subducting plate has a chance of having a continental mass on it. So we can go from an ocean to continental collision to a continental to continental collision. This convergence is much more complex in terms of what happens. It starts out as an ocean to continental. It starts this way. But then we have the continent come in. So what we'll see is this complex feature where we see the features of a continental ocean complex, and then they merge together, smash together, literally. And I want to find a decent one because I'm not going to try to draw this. Trust me, you don't want me drawing this one. Yeah, this will work. So this is in your book, page 473. So this is what happened with India coming in towards Asia, South Asia. So the subducting plate is coming in. You have the line of continental volcanic arc. You have the accretionary wedge that's scraping material off of the ocean floor. And then you have, once the plate actually smashes in, you start forcing the former continental material on the subducting plate under the overriding plate. Studies have shown that chunks of India have been shoved under Asia by as much as 2,000 miles. Not 2,000 miles down, but 2,000 miles horizontally under the Asian continent. This produces huge amounts of folding, huge amounts of faulting, massive amounts of metamorphic materials, because this is forming the regional metamorphism. It can create large amounts of granitic materials also with the forces that are involved. This has produced several mountain ranges in the world. The Appalachians used to be as big as the Himalayas, if not bigger, but they've been worn down over time. The same thing for the Alps, the same thing for the Urals. The Atlas Mountains are another mountain range that was formed through collision. They're all old. The new kid on the block from this process is the Himalayas. And this is how the tallest mountains in the world are actually formed, is through this continent-to-continent collision. After the subduction initiates, you're going to have partial melting of the rocks, which are going to generate volcanic arcs. After the continents collide, the subducted ocean plate will separate eventually from the continental block and continue downwards, and everything else is going to then just kind of come to a stop inside the collision zone. But it takes some time for that to happen. The Himalayas are still growing, and from all the evidence that we have right now, India is still driving into Asia. So that collision is still active. Then we have the transform boundary. These are the boundaries where the plates are just sliding past each other. They tend to be associated with the spreading ridges, where you have because the Earth is a curved surface and the ridges tend to try to be linear systems. There's areas of offset. So you get the curve is the spreading ridge is offset. So what that would look like real quick is if I draw two parallel lines as the spreading center. And I'm going to draw the arrows on here of motion. Like this. This is a spreading center. This is a spreading center. This is a spreading center. They do tend to be offset like this from time to time. It's just a matter of trying to put a linear structure on a curved surface. But we get right here, this area here would be a transform boundary. This very much like what is happening with the San Andreas Fault. The San Andreas Fault is a transform boundary. If you are on the west side of that boundary, you're on the Pacific plate trying to go north-northwest. If you're on the south side or the east side, you're on the North American plate trying to go south-southeast, essentially. So they're just moving past each other. Therefore, that's why they're called transforms. They're just transforming that motion. We've got all sorts of evidence that we can talk about for plate tectonics. We've touched on already the deep sea drilling project, where age dating the sediments and age dating the rocks. Again, the youngest sediments and youngest rocks are near the ridges. The oldest are further away. Basically the age of the basins, the oldest rocks in the basins, the thickness of the sediment. We actually have something that really is interesting, is that with GPS today, global positioning systems, we can actually measure these movements taking place very accurately. So we have that as an additional proof. We also have the hot spots, like Hawaii and Yellowstone, that show us this motion. But going back to the calculations, Hawaii recently has been shown to be moving northwesterly towards Japan at a rate of about 8.3 centimeters a year. So it's trying to move off in that direction. Whereas in Maryland, it's moving away from England at a rate of about 1.7 centimeters a year. So that's also interesting, is that the plates do not always move at the same speed. They're moving at different speeds in different areas, and that can actually control the way the continents are going to end up moving and even rotating over time. Now, unfortunately, no singular mechanism accounts for all the motions of the plates. Realistically speaking, this is probably one of those situations where the simplest answer is not the best answer. We agree that there is convective flow within the Earth that is going to be a partial part of the driving force of the plates. The slow motion of the plates in the mantle are driven by the unequal heating within the Earth, so that's pretty much it, but it doesn't account for everything. We have an idea of slab pull, which is the descending plate. Once it becomes so dense, because of its coolness, it's denser than the material surrounding it, so it's going to try to drag the rest of the plate down with it. There's ridge push, the idea that because the material is pushed up, it's trying to slide off. Those probably play some role in it, but they're probably not not the total answer in and of themselves. Regardless of what's happening, we know that it is happening. So we're still trying to understand it. We do know that that plate tectonics is the single most powerful idea in geology today. It ties everything together. I know I haven't really been able to bring it all to you, but just everything that we can think of, we can find a way to tie to plate tectonics when it comes to geology and the rock cycle. We know that in how the mantle is convecting may have a role in this, but exactly how the mantle is convecting, we're still trying to figure out. There's ideas of multiple layers of convection or a single layer of convection. All of that is still trying to be worked out. But let's talk about the importance of plate tectonics to wrap this up. It provides a unified explanation for the Earth's major superficial processes. It provides a framework for geologists to find the explanations for the geologic distribution of earthquakes, for volcanoes, for mountains. It provides an explanation for the distribution of life in the form of animals and plants over time, for the occurrence of economically significant deposits. While not completely understood, the theory of plate tectonics is nonetheless a dynamic and evolving model of the Earth's dynamic processes. Keep in mind, going back to the original discussion in this class, what a theory is in science. A theory is not an educated guess. A theory is a well-tested, widely accepted explanation of the facts. Our theory is constantly being tested and constantly being refined. Science is not trying to provide I shouldn't use the word straight, set, unchanging answers. Our answers are always changing because we understand that we don't understand it all. So we keep striving. We keep changing our theories. We keep tweaking the idea for plate tectonics to get it right. The more we learn, the more interesting the world becomes with plate tectonics. Again, you can explain so much with it. It's amazing how many different things actually tie into it, both from geology and geography standpoints. So I'm going to end it here, 51 minutes, a little longer than I would have liked to have gone, but again, this is a fairly dense subject to try to get through in this short of amount of time. So hopefully that will help. Again, as always, if you have questions when we get together for the virtual class, please ask them. If not, then ask them below. Ask them in the forum. Send me an email, however, and I'll talk to you guys later.